Hello! Yes. I'm Ed, and I'm going to talk tonight about chemistry, cake, and robots. As you can see, there's a picture of a cake up there, and I'd like to start with a small experiment. Each of you have paper and pencils. So what I'd like you to do is take a new page and draw a picture of a cake, a birthday cake, because it's the 5th anniversary of Science Slam this year. You've got 30 seconds. Start now. "15 seconds. "10. 5, 4, 3, 2, 1. Okay, thanks very much. Right, for the second part of the experiment, get ready for this. Take a new page, remember what you've drawn, and repeat it exactly as it is the first time you did it. Good luck. Same amount of time, 30 seconds, go. "15. 5, 4, 3, 2, 1. Okay, thank you very much. So you might be wondering why I'm asking you to draw cakes. Partly because it's dinner time and you might be hungry, but also because I'm a chemist. And chemistry, as the cliche goes, is very similar to cooking or even baking. So there's a lot of comparisons, and even though it's a cliche, I'd like to talk about why I think it's kind of similar. To start off, to bake a cake, you'd first look online for a recipe, buy the ingredients, set them out, set up your utensils, turn the oven on, follow the recipe exactly, and then 30 minutes later, you'll have a glorious chocolate sponge waiting for you to impress all your friends with. And if they like it, then they might ask you for the recipe. So with chemistry, it's pretty much exactly the same, especially the part about trying to impress your friends. So to do a reaction, you'd first look in the literature, in the whole body of what is known, for a reaction that interests you. You'd get the reagents set out, you'd set up the apparatus, and you'd follow the reaction procedure exactly as you find it. And then probably a few days later, you'll end up with your product exactly as you want it, pure, and you can impress your colleagues, your boss, and anticipate your own future greatness as a chemist. So this is generally how science works. You look in the literature and you find out something that you want to build upon, improve, and modify in some way. And with that, we get new discoveries, new chemicals, compounds coming out that improves our lives in ways that you often can't predict. So quite often there is a problem with this. And if you look back at the pictures you've drawn, you'll see that although the cakes are similar, they're not exactly the same. There'll be small differences that you can't control for. And although it doesn't matter here, if you're baking a cake, you could end up with more mistake than cake, making everybody sad. Whereas if you are in the lab, even if you follow somebody else's procedure exactly as they've written it, there's small idiosyncrasies that the researchers may have done and not put in their method, and you end up wasting valuable time trying to find out what went wrong and how to correct it. So this is particularly frustrating because we spend time trying to make new drugs or new greener plastics or new tiny bits in solar cells that make them that much more efficient that can change our world for the better. And all this time with quite incorrect syntheses can really hold us back. It's well known in cooking that this can happen. You can often follow a recipe that doesn't quite turn out as planned. But in science, almost everybody who works there has a story about somebody who couldn't follow someone else's synthesis, couldn't reproduce what they'd done. But the journal Nature, which is one of the most authoritative bodies in the science world, did a study on this to find out how big the problem was and whether it was just tales about people not being very good at the job. So what they found was quite interesting. Let me see. So they asked 1,500 researchers, is there a reproducibility crisis in science? And 52% said yes, and it's significant. Whereas a further over two-thirds said yes, there is. Only 3% said no, everything's fine, which is about the same amount who deny climate change. So I think there is about something going on here. So what do they mean there's a reproducibility crisis? Basically, they're asked, have you failed to reproduce an experiment? And what we see here is most scientists across the board have had the experience of not being able to reproduce something in the literature, either someone else's work or their own. Even in typical stalwarts of reproducibility like physics and engineering, they're still reporting high levels of this. The worst offenders are, of course, people in my own field, the chemists. So this is frustrating because it delays these important discoveries. In my own field, which is polyoxymetallate research, which are tiny metal oxide clusters, which range from anything from 25 atoms to 2,000 atoms. It's particularly bad because the syntheses that we do are very sensitive to minute details in temperature or pH of the reaction, or even small vibrations when you're trying to let your product purify itself can change the end product of what you get. To illustrate this, think of room temperature in Glasgow. It's going to be different to room temperature in, say, Barcelona. So a synthesis that says room temperature can give different results in these two different places, and this has happened, and it's been a problem. But even worse than that, room temperature in Glasgow is not the same throughout the year. In July, it's a lot warmer, and in December, it's a lot colder, or at least in theory it is, but we don't know. And that has an effect on the observations that we make. So people in my group and others throughout the world are thinking of ways to get around this. And one solution that we're working on is set up robotic systems where every parameter that we can think of is controlled in a closed system, so that we're recording everything and reporting everything. We then create digital recipes that we can then send to people across the world who can use the same systems and reproduce our results exactly. This is great. We're effectively making robot chefs. So the work that I'm doing is basically building a platform that's capable of doing reactions, stirring them, and isolating the product. And a digital recipe is as simple as just a file with all the reactions played out, and if they follow the program, then it forms the product exactly. So now that we've introduced robots into chemistry, what can we do with them? So one of the most obvious advantages is that robots don't need to sleep, unlike PhD students who unfortunately get a few 4 or 5 hours a night. They can have a high throughput, they can do more than one thing at a time, and they don't need to stop. They also, as I've said, can monitor temperature, pH, or even solution color, viscosity, or even surface tension. And with all of this, we get a much greater picture of what's going on in the reaction than we would with just a human watching it. Further, all of this information can then be fed into a computer machine learning algorithm, which can then with a better understanding that the machine has, it can use this to model the reaction system going on, and then come up with its own ideas about what reactions we should be trying, which is a very interesting concept that I'll talk about in a second. People in our group have been using this robotic system to do different types of experiments. Some people have been looking at what happens when you put oil droplets into a water system using a robot, and when they put them in, the oil droplets will dance around and do different patterns and all sorts of cool things. Using their robot and machine learning algorithms, they're able to identify 2 new behaviors of droplets that hadn't been seen before. Why is this interesting? What's so cool about droplets? Well, we think that life originated in droplets, possibly of oil or water. So this has implications about what could have been happening at the origin of life. Secondly, another of our colleagues has been seeing what happens if you have a robot challenge a human at their own game of chemical exploration and synthesis. The experimenter used an algorithm in a robot to look at the previous results and see who could explore more chemical space versus 2 human experimenters in our own lab. The robot won. Quite incredible. My own work is to go back to the digital recipe idea, where we can look at other groups' work, put it into digital form, and then send it across the world for anyone to reproduce. So I've been working on compounds that are useful in water oxidation and trying to get as reproducible as possible the ideal optimal synthesis that we can distribute. Aside from that, I've been trying to create new molecules using this system and similar learning algorithms. All of this goes back to the digital recipe, which can be passed on reliably. Second part of what I'm doing is perhaps the polar opposite of trying to have everything identical. We're looking at the inherent randomness of chemical systems, where you're choosing one reaction and repeating it mercilessly and watching how identical inputs can have different results, even in the same system and across time. So I've been looking at the crystallization of one particular polyoxymetallate that starts off just as initial reagents through a deterministic system, and the outcome is total chaos or non-determinism. And at the core of what chemistry is, that's what we're looking at. So, in summary, robots aren't going to replace humans in the lab or in many other areas, but they can augment what we're already doing. They can make us a lot better. So I say the future will be automated. And I think it's time that chemists had a piece of that cake.